I'm Sara Seager, an astrophysicist and a professor at the Massachusetts Institute of Technology. Welcome to my exp. The Kepler Space Telescope, which launched in the year 2009, was many decades in the making. It was actually finally made possible by CCDs, a type of detector. And Kepler changed everything. Kepler showed us that planets are incredibly common, that planets 2 to 3 times the size of Earth appear to be the most common planet in our galaxy. And Kepler showed us that small rocky planets are also very common. Rocky planets are the kind of planets that could host life. So Kepler was a game changer for the field of exoplanets. And exoplanets will continue to evolve and flourish each time there's a brand new telescope like Kepler. And right now we're all eagerly waiting for the next big telescope, which is called the James Webb Space Telescope. It's a telescope led by NASA and ESA and the Canadians, and this telescope will not find planets, but it will characterize planets. The characterization of a planet is quite crude, actually. We would like to know what the planet is made of on the inside, which parts of the basic building blocks we know planets are made of belong to a given planet. Like, is the planet mostly rocky? Does it have liquid water? Basic questions like that. Characterizing a planet also means trying to understand its atmosphere. The gases present, like for a small rocky planet, we'd like to know the temperature of the planet's surface. And for that, we need to understand the greenhouse gases present in the atmosphere. Right now, when we find planets, we know very little about them. We just know the planet size, we might know the planet mass, and we know the planet orbit, how far the planet is from the star, so we can also tell how much energy from the star lands on the planet. That's not very much, actually. We have so many planets, and we know so little about them. There's a very popular new planet, one that I actually proposed to observe. And the planets don't have very good names. The name is K2-18b. That means it's a Kepler planet from the second version of the Kepler mission finished, and when it was extended, it was called K2. And this is, I suppose, the 18th star with a planet that was found. What's so interesting about K2-18b is it is one of the mini Neptunes, the planet that's between 2 to 3 times the size of Earth, for which we have no solar system counterpart. We don't really know what they're made of. This planet is so interesting because it's a similar temperature to Earth, we think. And although this planet doesn't have a solid surface as we know it, the mini Neptunes are too big. They have a giant envelope of hydrogen and helium. What's very curious about this planet, K2-18b, is there is a small possibility that it has, beneath its atmosphere, that it has a liquid water ocean. These mini Neptunes are pretty crazy. If they happen to be made of a lot of water, they could have a liquid water ocean layer. And that ocean doesn't sit on top of a rocky layer, but it will sit atop a layer of like high pressure ice. So in my proposal, I wrote that, and I'm sure many people propose to look at this one object because it's bright and it's compelling. I propose to look for atmospheric gases that may or may not indicate the presence of an ocean. On my proposal, I have a core team of about 6 people who are very familiar with data analysis, like from the Hubble Space Telescope. And as a team, we have experience in observing planet atmospheres and looking for gas signatures. But my bigger team that works on the problem in general is very interdisciplinary. We have a biologist, 2 biochemists. We have experts in photochemistry in the atmosphere, a type of chemistry where the ultraviolet radiation from the star creates a cascade of different reactions. And we also have people who understand the Earth and the subsurface of the Earth and volcanoes and other things that might contribute to the atmosphere. Other than my team specifically, I am plugged into a much larger group of people who study high pressure of interiors of planets. Because if these mini Neptunes have deep water oceans sitting atop water ice, we have to understand how energy and materials can flow through these very high pressure materials for which we have really very limited understanding. So it takes a very broad array of people and of disciplines and of thinking to really try to get to the heart of the matter on any problem in exoplanets.